On these two problems, the directions are to assume that this procedure yields a binomial distribution with a trial repeated n times. Use the binomial probability formula to find the probability of x successes given the probability p of success on a single trial. And then round to 3 decimal places. Alright, so we have to remember our binomial probability distribution formula, or really I'll let you use a formula sheet so it's not a big deal. You don't really have to remember it. First we have that combination, n factorial over n minus x factorial times x factorial. Is that right? And then times, what's the next part? Anybody remember? P to the x times, now I told you this part could be written 2 ways. Either it's q to the n minus x, or you can think of it as 1 minus p to the n minus x. Alright. I guess we weren't given a q in the problem, but remember, q, if you so choose to make this part q, is the probability of failure. P here is the probability of success. So for this problem we'll have 5 factorial divided by 5 minus 2 factorial divided by 2 factorial times 0.7 to the second power times, what's 1 minus 0.7? 0.3, right? So 0.3 to the 5 minus 2 power, so to the third power. Alright? So a lot of this you can do in your calculator with, if you have a TI calculator, you can do this a lot faster than what I'm going to do it, but that'll be 5 factorial divided by 3 factorial times 2 factorial, or 5 factorial, I guess I could say 5 times 4 times 3 factorial divided by 3 factorial times 2 factorial, and then those would cancel out. 2 factorial is 2 times 1, 5 times 4 is 20, so 20 divided by 2 is 10. So this first part is 10. Alright, so this up here is going to be 10. Do I need to slow down?
No, I've already done it.
So far you got it right. Good. So 10 times, we have 0.7 squared. That's 0.49. Alright, times 0.3 cubed. Alright, so I'll do that in a calculator to make sure I don't mess up a decimal place. So you can say 0.3 on this Windows calculator. You have an X to the Y button, and so most calculators, if you don't have a little up caret for a power, then you use X to the Y or Y to the X button. So 0.3 X to the Y. You can even see it's kind of small on the Windows calculator. That creates a little up caret there, and that usually in math terminology means raised to the power of, and so we're going to raise that to the third power equals, so 0.027. Alright, so now we just multiply across. 10 times 0.49 times 0.027 equals. And so if I rounded that to 3 decimal places, I have 0.1323, so that would be 0.132. Alright. Now what we're figuring out is the probability of having exactly 2 successes on this problem. The x equals 2. So there were 5 trials run, and the probability of a successful trial, whatever it may be, is 0.7. And so we're figuring out the probability of exactly 2 successes out of 5 trials. Now let me show you something that's in the book. There are some tables that are in the back of your ebook that you can use with probability with binomial probability formulas, binomial probability distribution. The problem is that the tables don't have every success rate. So let me show you what I'm talking about. Alright, these tables, if you look at your ebook and you go to Appendix A and you go to page 799, you can see these tables are labeled binomial probabilities. Now, the reason why we don't always use these tables is because you can see up here at the top the P in these columns. I mean, that's not every success rate. That's just 0.1, 0.2, 0.3, so on and so forth. Okay? So if you do have a success rate that is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, or 0.8, you can go to the back, and if n isn't too large, so for example, the problem that we were working here, n was equal to 5, x was equal to 2, and the success rate was 0.7. So if I go to these tables and I go to n equals 5, that's right here on the tables. It's kind of hard to see. It may be a little small. And then a success of x equals 2 is right here. And then if I go over to 0.7, that's the column right here. That gives you 0.1323. So the answer is in the table without even having to do any calculations. Alright, now this table doesn't, it goes on for a while. You can see here's n equals 9, n equals 10, 11, 12, 13. Let's see how far it goes. There's 16, 17, 18, probably goes to about 20. There's 20. Yeah, and that's where it stops. So if your n is 20 or less, between 1 and 20, and your success rate is between it's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, or 0.8 or 0.9, then you can use the tables. Okay? So for example, on this next problem, you can work it out using the formula. You couldn't use the tables, though. I see right away n equals 30. So that means that we don't have an n equals 30 in the table. So we have to do this one out by hand. So this would be 30 factorial, that's a really big number, over 30 minus 12 factorial times 12 factorial. Alright, then I'm going to have 0.2 to the 12th power times 1 minus 0.2 is 0.8. That's going to be to the 30 minus 12th power. So that's to the 18th power. Alright, so this is going to be Alright, if I'm going to have 18 factorial right here, and then 12 factorial, so that means I would need to count this down. Ooh, that's a lot of numbers. All the way down to 18 factorial. Now, instead of writing all of those numbers, I'll punch them in the calculator. But I'm just going to put dot, dot, dot. I mean, I'm going to keep multiplying and going down until I get to 18 factorial. Then you can cancel those out. Now, I still have to divide that by 12 factorial. So what I'm going to do is I'm going to go ahead and do that in the calculator because that's a pretty big calculation. Alright. So 30 times 29 times 28 times 27 times 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19. 19 would be the last number there. Okay. And then I need to divide that by 12 factorial. So you should look for a factorial button on your calculator. Don't see one here. Yeah, I do. N factorial. So I'm going to put divided by 12 factorial equals. Alright, so you can see that's a really big number. That's 86,493,000. $225. Notice that it came out to be a whole number. The way that these factorials work out, you're going to get whole numbers whenever you work out the combination part. If you don't get a whole number, something went wrong. Now, some calculators can handle values like 30 factorial, but not all calculators can. So there's a chance if you have a real small, like scientific calculator, if you just tried to you didn't simplify, and then you tried to find 30 factorial, you can see even this calculator, it has plus 32. That means times 10 to the 32nd power. So you really need to simplify this first. Now, if your calculator can store that actual value, then it's okay to leave it like that. But if your calculator is rounding that off, that's going to cause some problems. But as long as you can get this 86,493,225, that's the main thing. Alright, so we have that number. That's just the combination part. So then we need to say that times 0.2 to the 12th, and then that times 0.8 to the 18th. Okay. So times 0.2 raised to the 12th times 0.8 raised to the 18th. Alright, so if I rounded that to 3 decimal places, I'd have 0.006. So what that means is, for this particular trial, whatever it is, there is a success rate of 0.2, 20%. That's what that is. And if you were to run 30 trials, and you wanted to know the probability of getting exactly 12 successes, that would be 0.006 or 0.6%. So a really small percentage. That's just what? That's 6 out of 1,000. Yes.
When I put in 0.2 to the 12, I get 4.096 e to the negative 9.
Okay, let's see. 0.2 to the 12. You get 4.096 times e to the negative 9. That means your calculator is storing that as, let me show you, 0.4096 times 10 to the negative 9th. That's what that means in your calculator. So if you needed to write that out, you would need to move the decimal place 9 places to the left. So that would be 8 zeros and then 4096. And so most calculators will only store up to about 8 or 9 digits. And so when they give you that times, or you see an E and a number after it, it just means scientific notation. But your calculator will actually store that number so that when you multiply that times 86,493,225, then that's going to be something that your calculator will display properly, that you should be able to understand. Okay. Alright, so that is what we've been working on. The binomial distribution. Now there is, I wanted to show you part of another problem, and this problem was out of your book. These first two parts are the easier parts, the expected value and the standard deviation. If you remember, we went over the formulas for those. What we've been doing is like part C here, exactly 2 or equals 2. But if we ever have to do a problem like this where it says at most 3 or at least 2 or less than 5, of course you have to understand what that is in math talk. Alright? And this problem does say to use the table. You do not have to use a table. It just means for every probability that we need to find, we'd have to work out a problem like we did one of those two. So let me show you what I'm talking about. So here on part D, it says find the probability that x is at most 3. At most 3 would mean 0, 1, 2, or 3. Right? So the probability that x is, and you can write as a capital X, is less than or equal to 3, that means at most 3, is equal to the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. So if we do this out by hand without using a table, we use n equals 9, then we would use x equals 0, p equals 0.1, 1 minus p equals 0.9, and we work out the problem like we did earlier. So we'd have to work out one for 0, work out one for 1, work out one for 2, work out one for 3, and then add all of those together. So you can see why it says use Appendix A, Table E, because it actually has values for n equals 9, p equals 0.1. So if I go to the e-book and I go to Table E, here's where n equals 9. Well, it actually starts, you can see the way this book is, it starts here. You because this is n equals 9, x equals 0. Now we need to make sure that we're in the right column. The success was, sorry. I'm not going to buy anything today. The success was 0.1. N was 9. And we need x equals 0, 1, 2, and 3. So we're going to get those from that table. So here is 9. That's n equals 9. That's x equals 0. Just need to make sure I'm in the right column. 0.1. So it's the first column. So I need to take that. 0.3874. Alright. Well, let me get to the... So this is 0.3874 plus, I need n equals 1, 0.3874 again. 0.3874 plus, now I have to go to the next page. Here's x equals 2, 0.1722. Plus x, the probability x equals exactly 3. So that's here, 0.0446. Okay, and so we add all of those up. All right, and so you can see that the probability is 0.9916. Now, what would E mean? At least 2. Let's think about that for a second. At least 2 means x is greater than or equal to 2. Now, at first, you may think, man, that's going to be a lot of work, right? Because that would be the probability that x equals 2 plus the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5, plus the probability that x equals 6, plus the probability that x equals 7, plus the probability that x equals 8, plus the probability that x equals 9. And if you attempt to work this problem like that, yes, it will take you a while, even by using values in the table. Imagine if you had to work out the binomial probability distribution formula with each one of these. You know, that may take me about 2 or 3 minutes, right? More like 20 or 30 minutes. But you have to remember the way that probabilities work. Remember, the sum of all the probabilities has to be equal to 1. So if we use that concept, then what we can actually do is we can say this answer right here, the probability that x is greater than or equal to 2, is actually equal to 1 minus the probability that of everything else, the other stuff. So the opposite of greater than or equal to 2 would be less than 2, right? That would include the other numbers. So the probability x is less than 2, or 1 minus the probability that x equals 0 plus the probability that x equals 1. Right, because that's everything else. If you ever get confused, you can always write it all down and then see what it actually means. And if it means something really long like this, we can always use the fact that all the probabilities have to add up to be 1. So since all of the probabilities have to add up to be 1, if we say 1 minus the opposite of what we need to find, then that will give us the same answer as working all of these out. So that's the smart way and the most efficient way to work this problem. Okay? So I would need to say 1 minus and then add those two up. So if I go back to the table, I'm here at 9, I need the probability for 0 and the probability for 1. And we've already found those. We found those in the other problem, right? So we do have them already written down. It's the 0.3874 and 0.3874. So if I say 1 minus that sum, let's see what I would get. I'm just going to subtract it twice. So 1 minus 0.3874 minus 0.3874, 0.2252. I do. But if I distribute that negative, it's going to be subtracting twice, right? Yeah. Throwing some math knowledge in there. You can still add those together and subtract them from 1. You get the same number. So 0.2252. So it's important that we understand this whole 1 minus concept because it could cut down on your work a lot. Otherwise, you're going to be sitting here, even if you use a table, you have to get all of these values from the table and add them up. Okay. The tables will make your lives easier as long as the values are there. For most of the problems that we work, if the n's not too big, they should be there. Okay, as long as the n's not bigger than 20 and the percentage is not something crazy, then, or the success rate, it should be there. Every once in a while though, you know, like we worked out at the beginning, this problem here, you see n is greater than 20. Or maybe p is not 0.1, maybe it's 0.17. Or maybe it's 0.05. So if p is not one of those values in the table, then you can't use the table, of course. Alright, so that finishes up the binomial probability distribution. Now I want to, and we have a table for this next part too, but we do need to understand what we're doing because, again, not all values are going to be given in a table. So there is a formula that we can use. And this is going to be on the Poisson distribution.